This video is about energy profiles. By the end of this video, you should understand how an energy profile represents the energy changes over the course of a reaction, and you should be able to label the parts of an energy profile. You should be able to do this for single-step mechanisms, for multi-step mechanisms, and for catalyzed reactions. An energy profile shows the energy changes over the course of a reaction. You'll see here that the y-axis represents energy, and the x-axis is kind of this weird thing called the reaction coordinate. It basically means like the progress of the reaction. Notice there's no values along the x-axis. It's kind of like time, but it doesn't actually follow a particular time unit. You can just think about it as the progress of the reaction from start to finish. A typical energy profile will have the energy of the reactants and the energy of the products. So if there were values along this energy axis here, you could actually determine what those energies are. And then as we know, in order to get from reactants to products, we have to achieve an activation energy, which is represented by this curve here. And so our activation energy is the difference between the energy of the reactants, where we start, and the energy you have to achieve in order to start becoming product. Remember, activation energy is abbreviated EA. Let's look at this in a bit more detail. So here's a full labeled energy profile. Let's look at the key parts. The key parts here are, again, the energy of the reactants, which notice in this case is lower than the energy of the products. In the previous example, it was higher. You might consider what the meaning of that is. We also have the energy gained or released by the reaction. This is our delta H. This is the difference in the energy, difference between the energy of the reactants and the energy of the products. In other words, the difference between where we start and where we end. As you may recall, we've looked at this before, the idea of endothermic and exothermic reactions. Endothermic reactions have a positive delta H, meaning energy is gained. So in this case, the products would be higher in energy than the reactants. A negative delta H would mean the opposite, that the products are lower in energy than the reactants, and the reaction loses energy. So the energy profile you're looking at here on the right is for an endothermic reaction. The one on the previous slide was for an exothermic reaction. We also see that the activation energy is labeled. The activation energy, again, is the minimum energy needed to initiate a reaction, and it's the difference between the energy of the reactants and the energy of the activated complex, which is a temporary arrangement of molecules at the peak of that activation energy barrier. It's a transition state, so it doesn't stick around for long. You can kind of think about, a good analogy here is to think about an energy profile like being a roller coaster. So you start out at ground level, you ride the roller coaster up, 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 putting energy in until you get to this top moment here, right? Think about that feeling in your stomach right at the very top of the roller coaster where you know you're about to drop. That's that temporary arrangement, that activated complex. There's no turning back from there. Once you're there, you're going. And that's how a reaction works too. Once the activated complex is achieved, once the activation energy is achieved, it's turning into product. There's no turning back. Let's look at two more specific examples. Here's a specific example for an exothermic reaction, the reaction between carbon monoxide and nitrogen dioxide to form CO2, NO, and release of energy. It's an exothermic reaction because energy is exiting the system. It's being produced by the reaction. So we see here the energy of the reactants, the CO and the NO2. When they collide with the proper orientation and the proper energy to overcome the activation energy barrier, they form this temporary arrangement of molecules called the activated complex, and then from there, they will convert to product. Notice in this case, the products are lower in energy than the reactants, so energy is released. Our delta H, our energy change of the reaction, will be negative because we're lower in energy at the end than we were at the beginning. Consider the reverse of this reaction, which is an endothermic process. Here, energy is being added to CO2 and NO to produce CO and NO2. This is literally just the flip of the previous reaction. Here, our reactants start down here. They're lower in energy than our products. We get that collision with proper orientation and energy, enough energy to achieve the activated complex. that temporary arrangement of molecules, and then we form product. In this case, energy is absorbed by the reaction because our products are higher in energy than our reactants, meaning it has a positive delta H. Let's practice labeling an energy profile. Pause the video here and see if you can determine which number on the graph corresponds to each of these values. Then decide if this energy profile represents an endothermic or exothermic reaction. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. The energy of the reactants is number 1. The energy of the products is number 5. Delta H is the difference between the energy of the reactants and products, so that's represented by 4. The activation energy is 3 because it's the difference between the energy of the reactants and the top of the activated complex. Number 2 is the energy of the activated complex. And finally, this is an exothermic reaction because we are losing energy. The products are lower in energy than the reactants. Now let's consider how a catalyst will change the energy profile. So as we should recall, a catalyst will lower the activation energy of a reaction. That means it will lower this green bump here. So it will not change the energy of the reactants or products, and therefore it does not change the delta H, since that's the difference between the energy of the reactants and the products. If we sketch this on the graph, we would see just a shorter activation energy bump, right? So our new activation energy is significantly lower. It would be like a roller coaster that's less tall. It takes less energy to get to the top, right? We can also consider energy profiles for multi-step reactions. So far, we've only been looking at single-step reactions, but if a reaction occurs in multiple steps, as we've seen in this unit, there's going to be an activation energy for each elementary step. So this one has 2 steps, so there's 2 activation energies and 2 transitional states. This is where the intermediate exists in the middle here. So this would be the first step, you achieve the activation energy, you get an intermediate, and then the second step, you achieve the activation energy to get product. The slowest step, which remember is the step that determines the rate, is going to be the one with the highest activation energy, which should make some intuitive sense, right? The one that has the highest activation energy barrier is going to go the slowest. And so in this case, that's this first step. This first step is the rate determining step because it has the highest activation energy. That would make this then the fast step because it has a lower activation energy. That brings us to the end of this video. Let's review our goals. First, we looked at how energy profiles represent energy changes over the course of a reaction. Then we looked at how to label the parts of an energy profile for catalyzed reactions, for single-step mechanisms, and for multi-step mechanisms.